To this, the fourth of the University of Birmingham Wind Engineering Seminars, sponsored by the International Association of Wind Engineering. For those of you who don't know me, my name is Chris Baker. I'm Emeritus Professor of Environmental Fluid Mechanics at the University of Birmingham in the United Kingdom. Before proceeding, I'd like to wish you all a happy Western New Year at any rate, in the hope that it might be an improvement on the one that's just passed. Today's seminar is entitled Development in Bridge Aerodynamics, and the main talk will be given by John Owen of the University of Nottingham, and that will be followed by 4 shorter presentations. I would like to take both Dr. Owen's talk and the shorter presentations together, and then we'll have discussion all together at the end. The house rules are quite simple. Could you keep your microphones on mute, please, and your video off to reduce bandwidth issues? And could you put any questions you have in the chat function? And Grace Yan in Missouri will collate those and get them to me, and I will then put them to the speakers. We have over 350 registrants for this particular seminar, so I would be expecting 1 or 2 more people to arrive over the next few minutes. There is also a live stream of this seminar going on YouTube, and if by any chance we exceed the limit of the number of connections we're allowed, people will be directed to that live stream. Okay, so I'd like to introduce the first speaker then. The first speaker, I have given permission to share screen, so could I ask Dr. Owen to share screen while I give the introduction, please, if you could. John Owen is an associate professor in the Department of Civil Engineering at the University of Nottingham, where he's been for 27 years, serving 2 terms as head of department. He's a past chair of the UK Wind Engineering Society and was co-chair of the 6th European and African Conference on Wind Engineering. John's principal research interests are in the field of dynamic responsive structures, to the wind, of course, and the use of dynamic data in structural health monitoring. He's been involved in monitoring the response of long-span bridges to wind for many years, initially leading the monitoring programme on the Keswick Bridge in Scotland, and more recently on the Forth Bridge, also in Scotland, and the Fumi Bridge in Vietnam. John's worked closely with colleagues in computational wind engineering to simulate the aeroelastic behaviour of bridge sections, and has led a number of wind tunnel studies on section and full aeroelastic bridge models. He was responsible for the design and commissioning of the atmospheric boundary layer wind tunnel at Nottingham. Most recently, John has been working on the resilience of infrastructure in typhoons, developing a risk-based methodology for networks in Vietnam. So I will hand over to John. I think he's shared the screen. Are you there, John?
Yep, I'm here, Chris.
Okay, you can put your video on so people can see you if they wish to, John. Or if you wish to, of course.
Yep, I've put my video on for those of you who regrettably want to actually look at me. Thank you very much, Chris, for the introduction. Thank you for the invite to give this presentation, and thank you very much, everybody, for coming this morning, this afternoon, this evening, wherever it is in your part of the world. As Chris has said, I'm going to be speaking today about some of the work we've been doing on monitoring of large bridges, and especially the aspects of that monitoring that relates to wind and wind response. And it would help if I could navigate my screen properly. So I'm going to talk about 3 bridges in particular. I'm going to talk about Keswick Bridge and pull out some ideas we found there about vortex-induced vibrations, and in particular talk about the follow-on work that we did. I then want to talk about something much more recent, which is monitoring we've been doing on the Forth Bridge. And there I just want to highlight in particular a response to a non-stationary wind event, and also some work we've done looking at the influence of uncertainty in wind field parameters on the buffeting response of the bridge. And then finally, I just spend a few moments talking about our most recent monitoring, which has been on Fumi Bridge in Ho Chi Minh City, and make some just comments about the wind-induced response of that bridge. Okay, so first of all, Keswick Bridge, and I'll just highlight a number of people who've been involved, were involved in this work. It wasn't just me on my own. And there's a picture of Kazakh Bridge. And Keswick Bridge is located in the north of Great Britain, right up in the northeast of Scotland. It's on this corner here. If we zoom in a little bit on the map, it's located just outside the city of Inverness, and the bridge itself is on this trunk road here, running across the junction between the Beauly Firth to the west and the Moray Firth to the northeast. And straight out in this direction is the North Sea. So that arrangement of water around the bridge is very influential in the way in which the wind hits the bridge and also the response of the bridge, as we'll see in a few moments. Just notice also this promontory of land here, and that's these low hills you can see in the top image on the right-hand side. We'll see that plays an important part in the wind climate. The Great Glen and the Loch Ness is down this direction, which is much lower. This valley here. Looking over towards the east, you'll see the Fetch is more open water and low hills in the distance to the south. So here's an image of the bridge. Total crossing length is just over 1 kilometre, but the main suspended span is 240 meters. Real importance for the aerodynamics of the bridge is its cross-sectional shape. It's a typical pie girder, so we've got deep edge girders about 3 meters deep, a flat plate across the top, 22 meters wide, and that causes all sorts of aerodynamic problems. So this is quite an old monitoring exercise. Indeed, it's the exercise that first got me into wind engineering. It was between September 90 and May 91. And we were basically looking at measuring the influence of spatially varying wind field on the bridge response. We had some very rudimentary instrumentation. We were just using cup and vane anemometers, 8 of them, which were located principally on lighting columns down the center line of the bridge. And also we were measuring the response using 4 servo accelerometers. We had a very simple data strategy, which is to record 10-minute records, save summary statistics, and then save raw data for selected records. So we've got in total about 24,000 statistics and about 5,000 records of data. As you'd expect, there is a variation of the response with the mean wind speed that's approximately second order. So these graphs show the root mean square of the mid-span acceleration plotted against the 10-minute mean wind speed, and you can see the approximate second order trend in the buffeting response. The second graph shows the normal component of the wind speed, and the points I just want to highlight are these points here, where we seem to be getting very much larger response than the background buffeting behavior of the bridge. If we look at the influence of wind direction on the wind climate and on the bridge response, which I plotted in these 2 diagrams, this is 10-minute mean wind speed plotted against direction, and we can see that we're getting strong winds that follow those open water fetches that are Beauly Firth to the west. We've got strong winds coming along there. To the southwest in the Great Glen, we've got strong winds coming up. It's the prevailing wind direction in the UK. But we're also getting some strong winds from the northeast coming off the North Sea straight down the Moray Firth. The influence in terms of response is shown on the right-hand figure. And of course, for the strong winds from the southwest and the west, we're getting quite large response here. But the very large response is associated with these winds coming down from the northeast, aligned directly with the with the Moray Firth. Now, when we look at those records in more details. So these are just 4 typical records where those responses are very large. And this, we believe, is due to vortex-induced vibrations. And the important thing to note is the large response occurs just in very short bursts. The longest is maybe 1 or 2 minutes in this record here. But typically, it's a response that builds gradually over 30 seconds or so, reaches a maximum, sustains that for a short period, and then decays away again. But clearly, looking at those 10-minute records, the data is non-stationary, and we need to take that into account when we process the data. So we did data analysis, which involved chopping the records up into shorter duration. So this is for 30-second records, and we can see that brings out more information about the peak response in the vortex shedding region. We also did some short time frequency analysis, so using autoregressive methods to estimate power spectral densities which were time varying. And that revealed very clearly that the response during these vortex shedding events was occurring in one dominant mode. And again, that was sort of circumstantial evidence that it was vortex-induced vibrations. Now, important for me was that we then went on to do some follow-on studies. We followed this up by using both CFD simulations and also wind tunnel testing. And we got very good agreement between the CFD simulation work we did and also the wind tunnel tests we did over in Nanyang Technological University in Singapore. Just to illustrate some of those effects and some interesting properties that we were learning from the CFD analysis in particular. Here I'm plotting some simulations of the flow field in terms of vorticity at different phase angles through the vortex shedding cycle. So just simple 90-degree phase angles. The left-hand images are for a static model. The right-hand images are for a dynamic model. And it's interesting just to contrast the two and to notice especially the difference in vorticity that we're getting beneath the deck towards the downwind edge. And there's a much stronger vorticity forming through the vortex shedding phase cycle in the dynamic model than the static model, indicating the influence of the motion-induced vortices. We're also able to use the wind field from the URAN's predictions to get the pressure on the surfaces of the deck. And we see again a strong influence of the vortex shedding process. So what I've done is color-coded these figures. The green is for wind speeds below the vortex shedding peak. The magenta is during the vortex shedding peak, and the blue is after the vortex shedding peak. And we can see that the pressure distributions both above and beneath the deck are similar when similar for wind speeds above and below the vortex shedding peak, but during the vortex shedding process, we're getting a marked change in the pressure coefficients, especially in the region directly beneath the deck and in that trailing half where these magenta lines are coming away. I'm sorry, the screen is very slow, my end, so it's not showing my mouse pointer quite right. But in this region here, we're getting a clear growth in that pressure during the growth of the vortex shedding peak. That was for the mean pressure distributions. We also looked at the fluctuating pressure distributions using proper orthogonal decomposition. And that showed more of an influence on the top of the deck, where we can see again the same color scheme, a very different first proper orthogonal decomposition mode, pod mode, for the vortex shedding peak compared to before and after the peak. Okay, so that was a very quick overview of some of the lessons that we learned from the monitoring of the Keswick Bridge, which really first got me into wind engineering. Now let me introduce some work that we've been doing on the Forth Road Bridge. As you can see, the Forth Road Bridge here in this image, it's a very different bridge to the Keswick Bridge. It's longer, it's a suspension bridge. The deck is a big open truss girder, and therefore got very different wind-induced response. Now we've been monitoring this bridge now Basically since 2013, as part of the GOSHM project, GNSS and Earth observation for the structural health monitoring of long-span bridges. This is a series of projects funded by the European Space Agency and in collaboration with a number of different partners, both overseas and in industry. And the aim was basically to evaluate the use of space-based assets for structural health monitoring of bridges. A little bit more about the Forth Road Bridge. It was opened in 1964. The total length of the bridge is 2.5 kilometers and the main span is 1,006 meters. It crosses the Firth of Forth. So it's located again in Scotland, just north this time of Edinburgh. And one of the things about the bridge is that its structural response is dominated by temperature and traffic. And that means if we're to try and understand the wind-induced behavior, we need to try and separate out those effects to get a representation of that. And we've been doing a lot of work on data analysis techniques, big data, and so on, in order to try and separate out the wind effects from the effects of temperature and traffic. But one thing I do note is that it's quite susceptible in the lateral direction to wind, and the owners of the bridge and the operators of the bridge are quite concerned about the level of stress that wind induces in the main girder, especially under that lateral response. This is a brief overview of the sensor system, or the latest sensor system. We've got a mix of high-spec GNSS receivers, low-priced GNSS receivers, integrated sensors where we've got both GNSS receivers and sorry about that. I'm not quite sure what the alarm was for. And also integrated receivers containing both triaxial accelerometers and GNSS sensors. We've got a number of triaxial ultrasonic anemometers on the bridge, and we've also got the weather stations that are owned and operated by the bridge operators. Data flow and data architecture, essentially very similar to what we did on Keswick, but we've developed it in terms of integrating Earth observation data and introduced a lot of data interrogation techniques so we can do model updating and produce both live and historic reports of the response. Now, let me say a little bit about the influence of traffic and temperature on the response, and I can illustrate that probably most easily with a couple of weeks of data from 2016. So these are 10-minute mean and RMS displacement statistics in the vertical direction. The top image shows the mean displacement, the bottom image shows the standard deviation. So it's probably good to think of those in terms of the static displacement and the dynamic displacement. And what we can see very clearly is a diurnal effect, a daily cycle that's caused by both traffic that adds to the weight of the bridge and also causes dynamic excitation, and temperature, which causes a sagging of the bridge over a slow cycle. And we can see both effects occurring in the mean, but in the dynamic response, it's dominated by traffic. And in the weekends, when there's less traffic on the bridge, we can see there's a lower dynamic response. So that's in the vertical direction. In the lateral direction, we don't see that effect of traffic and the effect of temperature. So there's no diurnal cycle in here, either in the mean or in the RMS, the dynamic response. But what we do see is the effect of wind. So a windstorm came through on this Sunday, Monday period on the 7th, 8th of August that month. And you can see a big drift in the mean wind response moving up to 1 meter sideways, accompanied by some dynamic excitation up to 200 millimeters RMS displacement due to the wind. That was a 2-week period. If we look on a 4-year period, we can see not only the daily cycle due to traffic and temperature, which is the extremes of the cycle, the low cycle here, but we also see this big cycle on an annual basis that shows the temperature effect of summer and winter. And that causes a much bigger variation in displacement. So we've got up to 600 millimeter displacement occurring because of the winter summer fluctuations in temperature. I'll also note this red dashed line here, and that corresponds to the point at which they opened the new Queen's Ferry crossing, the 4th replacement crossing. And at that point, most traffic was diverted off of the 4th Road Bridge and onto the new bridge. And so we see a clear change in behavior in terms of the fluctuations in the response about the annual trend. This is just a representation of the effect of temperature on the displacement, but I'm going to skip over that and go straight onto this slide, which shows why it's important for understanding the influence of the wind on the bridge response. So this is the mean vertical displacement over a 5-year period. The color coding represents different years. And what you can see, the variation of mean responsive wind speed, it's impossible to see a trend in the mean behavior, and that's because of the effect of temperature. Now, we have put together some data processing techniques using artificial neural networks and Bayesian updating techniques to extract that information, but I'm not going to talk about that now. But what we see in terms of the dynamic behavior in this right-hand figure is that once the traffic is removed from the bridge in the later years, 2019 and 2020, we can see that the effect of traffic on the dynamic response is removed, and we can see a clearer second order trend with the vertical dynamic response. The lateral response for all years, we've got a clear second order behavior, both in terms of the mean, the root mean squared, and the peak displacements. Just to highlight that there is an influence of the wind speed on the natural frequencies of the structure, both for the first lateral mode shown in the left-hand diagram and the first vertical mode in the right-hand diagram. So maybe not a significant trend, but there's a clear trend there that as we increase the wind speed, we're reducing the natural frequencies. Okay, that's an overview of a response and highlighting the influence of temperature and traffic information. And we've got to try and extract, the wind influence behavior from that. But let me highlight 2 specific aspects of the behavior of this bridge that I think are of interest. And the first is the response to a non-stationary event. And if we highlight the data from 2015, we can see in both the mean, the peak response, and the standard deviation of the response that we're getting an outlier. And I'm sorry, the internet is slowing down my mouse again, but this red circled point here is giving me an outlier. And we would sort of say, well, what's that caused by? Is that just an error in the measurement, or is something else happening? Well, let's have a look at that record. And that record falls within the period between midnight and 1 a.m. on the 9th of January, 2015. And this is a record of the heaving response and the lateral response during that hour-long period. We're plotting both the full response that we measured and a 1-minute moving average, which gives an approximation of the background response of the structure. And you can see that there's nothing particularly untoward in the heaving response, apart from, of course, there's a large response occurring, but it looks reasonably stationary. But if we look at the drift response, the lateral response, there's a sudden sharp increase, very rapid increase of almost 1 meter in the background response that lasts for about 7 or 8 minutes and then decays away again. And superimposed on top of that is a sudden dynamic response, plus or minus 1.5 meters, which looks something akin to a step response of the structure. If we highlight just the dynamic behavior for a moment, you can see that extreme pulse occurring here at about 36 minutes past midnight. Now, what was happening at that time on the bridge? Well, there was a big storm. It was Storm Elon. It was a big storm, but it wasn't anything atypical for a North Atlantic depression. It did cause a lot of damage in Scotland, a lot of vehicles blown over, including this vehicle here, which was blown over on the Forth Road Bridge, coincidentally at 36 minutes past midnight. And just to highlight in this synoptic chart, the black line that represents a convergence line, which could be of interest in explaining what's going on. This is some anemometer data. We didn't have the sonic anemometers in place at that time, so we were relying on the bridge master for this wind record. And we can see a very rapid increase in wind speed and a sudden sharp spike just after midnight on the 9th of January. We look at that hour-long record in terms of the wind data, and we see very clearly that it's a non-Gaussian wind record, and indeed it's non-stationary when we do measures of stationarity. What could that be caused by? Well, the assumption is that it's caused by some kind of very large gust, possibly associated with convective activity. So to investigate that further, we looked at the rainfall radar images from the UK, because we would expect strong convective activity to be often associated with periods of intense rainfall. So this is a sequence of rainfall radar images at 15-minute intervals across the UK from midnight till midnight 45. And we can see this band of intense rain passing the location of the bridge, which is highlighted by this white circle, at just past midnight. Zoom in a little bit more closely, and we can see that's associated within that band of rain is a very intense band of rainfall, a very narrow, intense band of rainfall. And at midnight 35, it's exactly lined up with the bridge. We superimpose those images, and you can see the tracking of that line goes almost straight over the bridge. And at midnight 30, we've got 133 millimeters per hour rainfall intensity, which for the UK is very high. Is that associated with thunderstorm activity? Well, if we look at a record of lightning strikes over Northwest Europe during that period and during that storm, we can see this pattern of lightning strikes moving across from Northwest Scotland, through Scotland, across the North Sea and into Germany. And it just happens that we're getting a series of strikes occurring in the Forth estuary here at exactly the point when we measured that extreme response on the bridge. So our supposition is that there was a squall line passing the bridge, which was generating extreme convective activity associated with thunderstorm cells that caused the gust front leading to that extreme response. One other thing I want to mention is work that we've done looking at the uncertainty in wind field parameters on the buffeting response of the Forth Road Bridge. And we were looking at this because we wanted to develop thresholds for structural health monitoring. And so we did some Monte Carlo simulation using the wind field variables as random variables. Most other things we were kept deterministic. We got the distributions to the random variables by processing the field data for 2018. And when we did that, we were able to recreate much of the uncertainty in the standard deviation of the lateral displacement that we measured on the bridge. So in this left-hand figure, we've got 1 year simulation data in red and 1 year monitoring data in black. And we can see the cloud of points lies on top of each other reasonably well. We can extend the Monte Carlo simulation, of course, for as long as we want. So we did for 500 years. And we can see the interesting thing is that the response increases quite significantly, but the corresponding wind speeds don't necessarily increase that much. And what we're able to do is to predict return periods for different levels of response at different wind speeds, and notice the shape of these return periods, that we can get events such as this record B and record A, which notionally have the same return period or very similar return periods, yet occur for very different wind speeds. And A, of course, has a much higher response for the same return period at a much lower wind speed. And if we compare the 99th centile wind speed prediction of the response using quasi-static theory with the 99th centile from the Monte Carlo simulation, we find that the Monte Carlo simulation is predicting a much bigger response, about 30% bigger than we get using just a simple quasi-steady analysis. Okay, finally, let me just say a few things about the Fumi Bridge, which is, again, a different context. We're getting out of Scotland and we're moving over to Vietnam. So Vietnam, a very rapidly developing country with a very different wind climate and a very different thermal climate to Scotland, and a very rapidly developing network of roads. So at the moment, they've got about 800, 1,000 kilometers of trunk network, hoping to grow that to 7,000 kilometers by the end of the decade. They've got a number of major cable-stayed bridges that they've built. They've got 14 in operation and another 3 in construction. And as part of that network of roads and bridges, they're putting together a network of structural health monitoring systems on those cable-stayed bridges. There's a number of bridges already on the network, and one particular bridge which isn't on the SHM network, but the one we're interested in, is the Fumi Bridge, which is in the south, in the vicinity of Ho Chi Minh City. So this was part of a 6-month feasibility study funded by Innovate UK and the Global Challenges Research Fund. And the aim was to try and explore using some of the data processing techniques that we developed as part of the GeoSHM project on the Forth Road Bridge to a different context in the Vietnamese situation. Now, this is a map of the environs of Ho Chi Minh City. The Fumi Bridge is a cable-stayed bridge. The main crossing is 705 meters long with a 380-meter long main span. It's about 11 years old, and it's part of the ring road around Ho Chi Minh City. And it's located here, crossing the Saigon River. And the important thing to note is the location of the bridge with respect to the city center. The city center is over here. I'm not going to talk about the instrumentation or the data sampling because I'm running out of time, but I want to just talk about some of the statistics of the response. Now, we principally just got accelerometers on this bridge, and this is just 1 week's worth of data from April 2020. And we're showing lateral acceleration and vertical acceleration. We're showing mean, and we're showing RMS. So the RMS is showing the dynamic behavior. And again, just as we did on the Forth Road Bridge, we're picking up a diurnal cycle, which is related to traffic loading on the bridge with quiescent periods at the weekend. And this day is a public holiday. The interesting thing is we're getting trends in the mean acceleration. Now, if you think mean acceleration, that's either due to gravity or something's happening to the bridge. And what we're thinking happening is either the bridge is twisting on a daily basis, or it is there's a change in slope on the bridge on a daily basis. So the lateral acceleration, any daily trend is showing us a twisting behavior. The vertical acceleration is showing us a vertical slope change of the bridge. What's that associated with? Well, if we superimpose every day on top of each other, we see there's a repeating pattern in that mean trend. Laterally, it grows slowly up until midday, drops off, and then grows slowly again. Vertical acceleration, it drops suddenly in the morning, reaches a trough mid-afternoon, and then grows back again. And that's repeatable day after day after day. Temperature is playing an important part in that. So we can look at the mean response against temperature, and we can see a definite correlation, especially in terms of the vertical response. But something interesting happens when we look at the wind data. So when we look at the wind data, these again 10-minute statistics for that same week, we see a strong diurnal feature in the wind record, both in terms of the along wind component, the wind speed, and also in terms of the direction. So this is the day by day by day, wind speed, wind direction, and then this is superimposing all those days on top of each other. And we can see that every afternoon there's a peak in the wind speed. And every afternoon the wind direction aligns exactly at -100 degrees, which is pretty much normal to the bridge deck alignment. And what we think is happening is we're seeing there the influence of a combination of the urban heat island and the sea breeze. So we're getting the wind switching from a random direction for most of the time, principally in the direction of the yellow arrow, but it varies quite a lot. But we get to mid-afternoon, it switches around to the red arrow direction. The sea is down here, the city center is here. So we've got a sea breeze exacerbated by the urban heat island that's generating a strong enough breeze to be picked up by the instrumentation here. And we think that might be contributing to the average response change that we're seeing. So I'll just leave you with a very few summary comments, nothing specifically detailed, but it's so what has monitoring of large bridges done for me? Well, it's been an opportunity to observe phenomena in the field, vortex-induced vibration, buffeting, non-stationary response, and to learn from those. It's been a springboard to further research, especially in terms of data processing, data analysis, computational simulations, and wind tunnel testing. And it's also exposed, I think, limits to many of the assumptions that are made in the analysis and design of these structures, such as stationarity, linearity, assumption of the process is Gaussian, and the modeling of uncertainty. Thank you very much to you for listening, and thank you to various research sponsors, collaborators, and people who've done all of the hard work on this. Thank you.
Thank you.